Hello everyone, I am John Valenton.
Hi, I'm Jandale David Joaquin.
Hi, I'm John Robert Lara.
Hello everyone, my name is Christian Rambuyon. This is Group 1 presenting. We will discuss about noise, types of noise, and how noise can be computed. Now first, what is noise? Noise is an annoying tone which causes serious discomfort or irritation. Although noise is similar to sound, their difference is that noise produces an unwanted sound. Noise is a kind of sound and is therefore described as annoying, irritating, unpleasant, or loud. As noise still produces sound, it can be measured. The unit of sound or noise is in decibels. The highest decibel measured is the takeoff of a jet within 25 meters, which is recorded to be 150 decibels. While the lowest noise measured is breathing, which is recorded at 10 decibels. Radio waves, power lines, and bad connections can generate noise in communications. Noise refers to any external or unneeded information that tries to interfere with a signal transmission. Noise can reduce the transmission strength and disrupt the overall efficiency of communication. Hiss sounds in radio receivers, buzz sounds in the middle of telephone conversations, and flicker in TV receivers are the most typical examples of noise. In telecommunications, noise can affect receiver sensitivity. Noise that people who haven't produced it experience is called second-hand noise. Similar to second-hand smoke, second-hand noise can have negative impacts on people. The noise is not only that is unwanted, but also it has a negative impact on human health. Noise-related symptoms include loss of hearing, stress, high blood pressure, lack of sleep, distraction, and loss of productivity, and a general decline in quality of life and opportunities for peace of mind. Exposure to continuous or excessive noise is shown to cause a number of health issues ranging from fatigue, impaired attention, occupational productivity losses, coping difficulties, and tiredness due to lack of sleep, to more severe conditions such as cardiovascular disease, cognitive impairment, tinnitus, and hearing loss. As there is pollution in the environment, noise pollution has been increasing as well over these past few years. Exposure to constant noise beyond 85 decibels for more than 8 hours can be highly dangerous. Let us discuss the types of noise. There are two types of noise, external and internal noise. First, let us discuss external noise. The noise whose sources are external to the receiver come under heading of external noise, extraterrestrial noise, and man-made noise. Now, under external noise, there is atmospheric noise, or static, is caused by lightning discharges in thunderstorms and other electrical disturbances occurring in the atmosphere. These electrical impulses are random in nature. Hence, the energy is spread over the complete frequency spectrum used for radio communication. Next is extraterrestrial noise. An example of this is solar noise. This is the electrical noise emanating from the sun. Under quiet condition, there is a steady radiation of noise from the sun. This results because the sun is a large body at a very high temperature and radiates electrical energy in the form of a noise over a very wide frequency spectrum, including the spectrum used for radio communication. Also, we have cosmic noise. Distant stars are also suns and have high temperatures. These stars therefore radiate noise in the same way as our sun. The noise received from these radiant stars is thermal noise, or a black body noise, and is disturbing almost uniformly over the entire sky. We also receive noise from the center of our own galaxy, which is the Milky Way, from other distant galaxies, and from other virtual point sources, such as quasars and pulsars. Also, we have man made noise, which is also known as industrial noise, meant the electrical noise produced by such sources as automobiles and aircraft, ignition, electrical motors, and switchgears, leakage from high voltage lines, fluorescent lights, and numerous other heavy electrical machines. Such noises are produced by the arc discharge taking place during the operation of these machines. Such man-made noise is most extensive in industrial and densely populated areas, such as cities and such.
I am John Valenton and I am going to report the subtopic of types of noise, which is the internal noise. So earlier in the video, external noise has already been discussed. So now, let's learn what internal noise is all about. Internal noise. It can be easily evaluated mathematically and can be reduced to a great extent by proper design. Internal noise was created by any of the active or passive devices found in receivers. Such noise is generally random. It is impossible to treat on an individual voltage basis, but it is easier to observe and describe statistically. Under the internal noise, there are these thermal noise, shot noise, transit time noise, and miscellaneous internal noise that will be discussed on the latter part. Thermal noise. It is also known as the Johnson-Nyquist noise, Johnson noise, or Nyquist noise. It is a phenomenon also known as thermal agitation, which is due to the random motion of free electrons in a conducting material caused by heat. Thermal noise is always present in electronic circuits and it is one of the major sources of noise. In RF circuits, it is often a critical parameter, especially for the front-end receiver circuits where it is key design parameters. The next is the shot noise. Shot noise is a form of noise that arises because of the discrete nature of the charges carried by the charge carriers, electrons, or holes. It can be seen that it is particularly obvious when current levels are low. This is because the statistical nature of the current flow together with the discrete charge levels is more apparent. Moreover, it is particularly noticeable in semiconductor devices, such as tunnel junctions, Schottky barrier diodes, and PN junctions. The next one is the transit time noise. It is the duration of time that it takes for a current carrier, such as a hole or current, to move from the input to the output. So these devices themselves are very tiny, so the distances involved are very minimal. Yet, time it takes for the current carriers to move even a short distance is finite. Miscellaneous internal noise. There are three noise that corresponds with the miscellaneous: the flicker noise, transistor thermal noise, and the partition noise. The first one is the flicker noise. It is sometimes called as the 1/f noise, the one appearing in transistors operating at low audio frequencies. So in semiconductor device, the flicker noise is generated due to the fluctuation in the carrier density. The mean square of the flicker noise voltage is proportional to the square of direct current flowing through the device. The next one is the transistor thermal noise. Within the transistor, thermal noise is caused by the emitter, base, and collector internal resistances. Out of these three regions, the base region contributes maximum thermal noise. Partition noise. It occurs whenever current has to divide between two or more paths, and the results from the random fluctuations in the division. It would be expected, therefore, that a diode would be less noisy than a transistor if the third electrode draws current. It is for this reason that the inputs of microwave receivers are often taken directly to into diode mixers. So with that, let's have a very small recap. Internal noise, there are four main parts of it: the thermal noise, the shot noise, transit time noise, miscellaneous internal noise. And with under the miscellaneous internal noise, there are these flicker noise, transistor thermal noise, and the partition noise. Thank you.
Noise computation. So John and I will discuss about noise computation. Let's start with noise power. Noise power is an interfering and unwanted power in an electrical device or system. So it can be expressed mathematically as Pn is equals to K times T times B. So Pn is the noise power measured in watts. The unit is watts. So K is Boltzmann constant. So 1.38 times 10 raised to negative 23 joules per Kelvin. So T is equivalent to noise temperature of the receiver. So unit is Kelvin. So if you have problems, so here's an example of noise power. So calculate the noise power in a room temperature with a bandwidth of 50 megahertz. So we will using the power formula for noise power, which is K times T times P. So K is the constant, so 1.38 times 10 raised to negative 23 joules per Kelvin. Then T is 290, which is said in the problem, room temperature. Then uh, B is for bandwidth, so 50 megahertz. 50 times 10 raised to 6 hertz. So the answer is 2.001 times 10 raised to negative 14 watts. Another one is calculate the noise power available from any resistor at room temperature for a bandwidth of 1 megahertz. So the formula again is P is equals to KTB. So 1.38 times 10 raised to negative 23, sorry, times 290 Kelvin times 1 megahertz. So 1 megahertz 1 times 10 raised to 6. So the answer is 400,200 watts. So next one is noise voltage. So noise voltage uh, is the voltage that is carried by the noise happening in the circuit. So the the formula will be V squared is equals to 4KT RB. And if you want the RMS value, B is equals to square root of 4KT RB, as B is the voltage, K is the Boltzmann constant, T is the noise temperature, R will be the resistance in the circuit, and B is the noise bandwidth. For example, calculate the noise voltage available from 20 ohms resistor at room temperature for a bandwidth of 1 megahertz. So the formula is square root of 4k TBR. So our working equation will be square root of 1.38 times 10 raised to negative 23 times 290 times 1 megahertz, or 1 times 10 raised. The answer will be 1.557 or 1.56 micro voltage microvolts. So noise density or power spectrum density. The definition is average noise power per hertz of bandwidth, or a figure that determines the amount of noise contained in specified bandwidth. So the formula is N sub O is equals to P N over B or equal to KP. So noise density is N sub O, which is the unit is watts per hertz. That's the definition. Pn is the noise power, B is the bandwidth of the noise spectrum, then T is the temperature. So, for example, you have bandwidth of 10 gigahertz and temperature of 35 degrees Celsius. So, first find the noise power. So, noise power is 1.38 times 10 raised to negative 23 times 35 plus 273.15 because 35 degrees Celsius is in Celsius, so we need to convert it to Kelvin. So times 10 gigahertz. So 10 gigahertz is 10 times 10 raised to negative 9. So the answer is 4.25247 times 10 raised to negative 11. So noise density will be Pn over B or equal to Kp. So the noise density will be 4.25247 times 10 raised to negative 11 over 10 times 10 raised to 9. So the answer will be 4.25247 times 10 raised to negative 21.
Noise factor and noise figure are figures of merit used to indicate how much signal to noise ratio deteriorates as signal passes through a circuit or series of circuits. Noise factor is simply the ratio of input signal to noise ratio to output signal to noise ratio. Ratio figure is simply the noise factor stated in dB or decibels. In this example, we will calculate the signal to noise ratio at the amplifier output. We are given a signal to noise ratio of input of 40 decibels and a noise figure of 20 decibels. So the equation that we're going to use is noise figure is equals to input or the signal to noise ratio input minus the signal to noise ratio output. So since we're looking for the signal to noise ratio at the output, we're going to do some algebraic manipulation, and then after doing that, we're going to solve now for the signal to noise output ratio, which is 40 minus 20, which we will get 20 decibels. In the next example, we were given a unit of power. So we're going to use in this problem, we're going to use the signal to noise ratio of general formula that is expressed by signal over noise is equals to power of signal over power of noise. First, we need to find the input of the signal to noise ratio, which is equals to power of the input signal and the power over the power of the input noise, which is 150 microwatts all over 1.5 microwatts, which is equals to 100. Next, we're going to solve for the output of the signal noise ratio, which is equals to power of the signal output over the power of the noise output, which is equals to 1.5 watts all over 40 milliwatts, which is equals to 37.5. After solving for the input of the signal to noise ratio and the signal to noise output ratio, we're now going to solve for the noise factor and the noise figure. So for the formula of noise factor, we just need to divide the input to the output. So 100 all over 37.5, which is equals to 2.6. So after finding the noise factor, we can now solve for the noise figure, which is in a formula of 10 log f, which is f is equals for the noise factor. So 10 log of 2.66, which is equals to 4.26 decibels. Another computation in noise is the equivalent noise temperature. The formula used is T EQ is equals to TO times F minus 1, wherein the TEQ is the equivalent noise temperature in Kelvin, and the TO is the reference absolute temperature, which is usually in 290 Kelvin, and the F is for the noise factor. So in this example, we're going to solve for the equivalent noise temperature. We are given of a noise figure of 3 decibels. So in order to solve for this problem, we need first to find the noise factor of the problem. Using the equation for the noise figure 10 log f, which f is equals to the noise factor, we can solve this problem. By using some manipulation, we arrive with the equation of f, or noise factor, is equals to 20 log of noise figure over 10. By simply putting 3 decibels in the equation, we arrive with the answer of noise factor is equals to 2. After that, we now solve the noise temperature. So using the equation, the equivalent noise temperature, TEQ is equals to F minus 1 times the reference temperature. So by the room temp is equals to 300 K, which is the reference temperature. By inputting the formula, or the noise factor in the formula, the equivalent noise temperature is equals to 300.